Good afternoon to all of you. So we are again back to the live session 2 for this course Fundamentals of Compressible Flow. By now this course has already been completed, all the lectures, and in fact all the assignments, all the modules, everything is over. So it is now your duty to uh, tell me if you have any queries about this course, so that we can, for next 1 hour, we can have some discussion. So as of now, we find only 4 people. So before you think about the question and pose the question, let me go through some of these forum queries that people have raised, and I'll try my best to find out some of the answers. Okay. So one of the questions that was raised in the forum was that while discussing the Mach number, we say that this Mach number is a function of velocity of the body or the gas divided by the speed of sound. So in this question, the query that was asked, what are the properties that are being discussed here? So here the first thing that the property is that it's a speed of sound A, and it is nothing but gamma RT. And the compressible flow theory, this speed of sound is also taken as the property of the gas, because it's a function of gamma, which is the specific heat ratio of the gas, or it is air, it is 1.4, R, characteristics gas constant, and the temperature. So if you see for a given medium or gas, this value is fixed, because all are because the A is function of square root of gamma RT, and in sometimes if you take some realistic number for air, that is gamma for 1.4, R is equal to 87 and T is equal to room temperature about 290 Kelvin. So this will be about 340 meter per second. So here the properties that are referred here is the speed of sound, and typically it is fixed at a given flow conditions or given conditions. But what happens is that means this Mach number can be increased just by increasing the velocity. So under these conditions, we can say that the speed of the sound is a property of the gas, and Mach number can be increased with the increasing the speed. Now the other side of the story is that now if you look at mathematically, this Mach number can be written as a function of V and A, and if I can write also, this is square root of gamma RT. So theoretically, I can change this Mach number by changing the speed of the body, or V, as well as speed of gamma R and T. If they change, I can Mach number also can be changed. So not necessarily that always change of speed of the body will change the Mach number. So in some situations, what happens is that in a very high temperature medium, something out when temperature is more than 1000 degrees centigrade or so, then under those cases, this effect of dissociation comes into picture. So due to this, the gamma changes are both of them are changes. So when they change due to this temperature, so effectively all the parameters in the denominator of this expression changes. So as a result, the Mach number also and side by side the velocity also can change. So when we are looking at the Mach number at high temperature limit, so no longer it is the velocity or it is not only the velocity, we also have to take into account the property of the gas that changes with the temperatures. So due to this reason we can say that the flow properties are dependent on velocity of the body as well as the properties of the medium. So I think this is the answer which was explained by me in this query. So uh, that's what I am trying to say. I am also requesting you please pose questions so I can answer one by one if they have. So anyway, let me go to another question that was raised, that was on uh, this Mollier diagram. So in the Mollier diagram, the query was what happens with increase in the increase or decrease in the static pressure ratio. So if you thermodynamically if you look at Mollier diagram, so this is a plot between enthalpy and entropy. So in this enthalpy and entropy plot, we are talking about the pressure. So constant pressure lines can be drawn in this manner. So these are the constant pressure lines, two constant pressure lines I have drawn here. So in this plot, what we are trying to say is that if we are going on this side, we are going in the increasing pressure line. That means pressure increases along if you go in this arrow direction. So what happens on this diagram, you take a particular point 1. Okay, so for this point 1 we are trying to say its enthalpy value we can say write H1 and S1. Now the question that was raised, that what happens is the static pressure decreases or increases. So the static pressure can increase or decrease. Uh, that thing is linked with the velocity of the flow. So what does this mean is that, so for this point, if you say that this is the static pressure line P1, and corresponding to this point, if I go along this constant entropy line, so I will reach the point which is P0, which is not condition, so it is called as total condition. So I will say corresponding to this number we have H01. So and this line will be P01. So constant pressure line, which is the stagnation pressure line. So here by definition we can say in the y-axis, for this corresponding to this point we say this is the static enthalpy H1, and for this from 1 to 0.0 I will say this is the dynamic enthalpy which you can write as u square by twice u square by 2. That means this is the kinetic energy part, this is the enthalpy part. Now what happens, the question here, that what happens if the static pressure decreases or increases. Now if the velocity increases, if u increases, so that means I am accelerating the flow. When I am accelerating the flow, if u increases, the pressure must decrease. Okay, so this is a situation we say it's a diffuser action, and in other side that if pressure increases, the velocity must, sorry, the first one is the nozzle action, increasing the velocity, and the second one will be decreasing the velocity, will be a diffuser action. Okay, again I am repeating, please send some of the questions, or I will keep discussing with these certain facts. Uh, the another question that was raised is with respect to one particular problem on pitot tube. But before I talk that about pitot tube problems, let me give you the concept of moving shock and stationary shock. And this is very vital as far as this course is concerned, that how you view this phenomena of this shock wave. Now when I say a shock wave is moving in a flow field, so I say that's a normal shock, it is moving in a flow field or flow domain. What I say is that, so it means that this particular shock is moving in a medium. Let's say this is air. Now an entire medium which is initially at certain conditions P1, T1, O1, maybe density, pressure and temperatures. This is the initial condition. Now somewhere the shock wave generated somewhere and it enters to this medium. So when it is entering and moving in this medium, what happens? As and when it passes, because of the shock wave, there will be rise in the pressure. So since this particular zone has already seen this shock wave, so medium is, the pressure, temperature and density is already enhanced. So this pressure becomes now P2, temperature becomes now T2 and density becomes now ρ2. So this is how, this means that this medium, temperature, pressure and density, they are already elevated, and accordingly we say that it is P2, T2 and ρ2. Now with respect to this moving shock phenomena, we say that this condition or this initial condition, and this is the initial condition and this is, we say, final condition. And with respect to the shock wave moving shock terminology, we say this initial condition as ahead of the shock, and final condition becomes behind the shock, which means ahead of the shock, whatever gas is there in that medium, it has not seen the shock wave, so it remains as its own initial conditions. So when I say behind the shock, that means the shock wave has already crossed that medium, so the gas is already in the medium, is as the pressure or flow condition or parameter has already been elevated. So this is the terminology we can say moving behind the shock and ahead of the shock. So in same concept, if I say this similar thing as a stationary shock, so when I say this is a stationary shock, so it means, so here what you are viewing is that shock wave is stationary, so the gas is coming and that gas is passing through the shock wave and it is leaving. So when this gas is coming, so we say it is its initial condition P1, T1 and rho 1. When it is leaving, it is the final condition P2, T2 and rho 2. And this shock wave is a stationary. So means that, so here it is the gas that is before the shock wave, and this is the gas condition after the shock wave. So these two things has to be very precisely understood to solve any kind of the problems. So in this, how they are related is that I mean, in a practical utility forum, I can say that when I am doing some wind tunnel test, in a supersonic wind tunnel test, what we can see that we can view this as a test section where some model is mounted. Let's say in this case, it is our pitot probe, and this measures some pressure of the flow. So that means this side some supersonic flow is coming. So this supersonic flow is moving in a medium that is air. So the air, when it is moving in this medium, so obviously there will be a shock wave when it sees this particular body, or this, we say it's a pitot probe. So this is similar to a situation that at one particular time instant, if I view this phenomena, we say that as if there is a shock wave sitting on this front of the body, and the shock wave is close to a normal shock, close to at the stagnation line or at the central line of the probe, and the initial condition of the gas was initially, if you say it's a standing shock, so the condition which is initially it was like P1, T1 and rho 1, and condition which is after the shock it becomes P2, T2 and rho 2. This is how when you see on the shock waves, when you see it on the shock wave and see the flow which is coming into this and coming and going after this shock wave, after it passes the shock wave. But when we are doing the experiment and we are looking at this particular phenomena from the test section window of the wind tunnel, then we can see this particular situation is like a moving shock. So that means this is something like a shock wave is moving, and as and when it moves, it changes the flow conditions. So that is the reason this explanation was given in this particular forum, and I have tried to explain. Another point I would like to mention that across this shock wave, there is a total pressure drops. So total pressure drops means there is a always increase in the entropy. So this point was I tried to emphasize on this forum question answer session. So the next question that was asked about, okay, that was something about the flow through nozzle. And the flow through nozzle, when you say nozzle flow, this is a very vital component of the aerodynamic experiments handled in the wind tunnel. So typically, when you look at the nozzle flow, we say there are two conditions, and a nozzle in a supersonic flow, it is just attached before the test section of the model, So this is just a skeleton of this nozzle, supersonic nozzle, and this is the inlet condition, and this is the exit condition. Now in this inlet condition is typically fixed by stagnation properties. And in this case we call this as a P naught, T naught, where rho naught means total pressure, total temperature and total density. Of course we have initial conditions like P1, T1 and rho 1, so many things. And the flow is, we are trying to expand this flow in the nozzle so that we want a desired Mach number. Suppose I say this is a nozzle and it is used for Mach 6 case. So obviously at the exit case what I am going to have is that will expect that I should get a Mach 6 flow at the exit of the nozzle, so that rest of my test section will see a Mach 6 flow. Now to the very vital part of this here, the design of this nozzle depends on the two important concepts. First thing is area ratio, other is the pressure ratio. So area ratio is a kind of a geometrical configurations. So this is with respect to nozzle. So I say this is the inlet area, this is the exit area, and the minimum area is I say throat. Okay, so these are the three important area that decides the flow in this test section. So based on that we say we have area Mach number relation. And we also have, for supersonic flow condition, we have the exit condition by total condition, pressure ratio. We also have this exit pressure to this total pressure, exit temperature to the total temperature. So these conditions are already known for supersonic flow. So the very basic fact that what is the minimum area, what is the minimum, and in fact this exit condition is typically controlled through by back pressure mechanism. So back pressure mechanism means that this exit condition is typically attached to some kind of a vacuum pump where we take out the pressure and its pressure gets reduced so that we can have a desired Mach number. So what is the most important is that for this Mach 6 nozzle we have a fixed throat area to the exit area relation. So this relation has to be satisfied. So this is one of the conditions, but it is not the sufficient conditions. So, but to have one of these Mach 6 flow, we also have to satisfy the PE by P naught ratio, and which is fixed, which is given as a function of Mach number for a supersonic nozzle, supersonic flow. So it means that, for example, if I say Mach 3.5 flow, this number will be about P naught by PE would be about 76. So it means that apart from satisfying the area ratio, I must take this pressure ratio as 76, and if I maintain this pressure ratio much high, then still I will be able to reach only Mach 3.5. I cannot increase this Mach number, because that point of time it is governed through area ratio. And in the other side of the story is that if you don't put 76, if if this number is still below, then I will not get the Mach number will be always less than 3.5 if P naught by PE is any number less than 76. So this is not the sufficient condition. So this is the query that was there is that what is the minimum pressure ratio you must maintain. So minimum pressure ratio in this case it is 76. And in fact it was elaborated in more details in this case. And there is similar to this, there is another concept that what is the terminology used for static temperature and total temperature. In fact both are of same meaning. So another query that was a very conceptual thing, so in fact it is based on the shock tube case. So in a shock tube flow, we say that there is a driver section, there is a driven section, and there is a diaphragm which is in between. Now when this diaphragm is ruptured, a shock wave is generated and it flows into the driven section. But this is the question that was there, that when there is a shock wave that is moving in the driven section, why there will an expansion wave that is comes towards driver section. So this concept was realized that whenever the formation of shock wave and expansion waves, they are exactly the opposite side of the coin. So what we can say, whenever a medium is pressure gets increased through the formation of the shock wave, then we say that medium is pressurized. Subsequently, when the medium is pressurized, whatever the other part of this side, that like in this case the driver side, this pressure gets reduced. So we say that this is a situation that we can have expansion fan that comes in the opposite directions. So we say that whenever there is a expansion fan always is created, and that these expansion fans moves towards driver sections. So this is a similar phenomena that the shock waves moves towards driven section and expansion waves moves towards driver section, because this driver section gas pressure gets reduced, driven section gas pressure is increased. And another question was the discontinuity in a flow feed. The word discontinuity refers to the fact that it's a kind of a sudden rise in the property conditions. So I can say it's a situation of a step function, or it can be like there is a property increase, it can be of impulse function. So what does this mean? That if you look at the event just t much less than 0, and you can just see this event t just slightly greater than 0, maybe t is equal to okay, I'll put a number like t is 0.9999 and t is equal to 1.0001. So if you see the difference between these two times is very small, but there is a event that happens, that is rise in some value, property value. So that we call it as a discontinuity. Now with respect to this fluid mechanics term or compressible flow theory, we say that the nature of the shock wave follows it as a step, because so in this entire flow field, just before the shock wave, we can say isentropic, and just after this flow field we say this is also isentropic. But what is not isentropic is the phenomena that is within this shock layer, which is about 10 to the power minus 5 meter thickness. So it means that within this small space or domain, this this entire event happens, and all the flow properties value we cannot find out, and it is not isentropic, and because of this reason we say that the shock wave phenomena is a discontinuity in the medium. So this is how we explain all the cases. Okay, in the fluid mechanics purview, only we have learnt that the shock wave phenomena is the only way that we can have a discontinuity in the flow field. But still there is some query that if the same guy is available here, they can specifically write what are the other conditions or other issues they are having. So I think I have explained all of these three things, and if there are any issues still far, one can pose. I think no question is available so far to me. So in this course, we have basically solved all the assignments, all the lectures, and it has already been completed, and down the line we will have the final exam. So all this final exam question paper will be of similar nature what we have in the main, similar to those of assignment in nature. So if you have any questions, please pose. Otherwise, I accept my wishes that you all do well in the exam, those who have registered for this course, and we may see in future for some other applicants. Okay, thank you very much for your attention. We are closing this session. Thank you.